Hi teammates, it's Mr. Ninny coming to you with what is probably the last physics bunker production for this school year. And bittersweet, I've mostly enjoyed doing these, except when I've had to do retakes. I still haven't, that's my goal for the rest of the summer, is figure out how to edit videos so I don't have to retake. I know it's not hard. I just need to sit down and figure it out. So let's look at the escape velocity problem. We had a problem yesterday I left you with to determine the escape velocity from Mars. And you saw the derivation, and the key fact is the mass of the object doesn't matter. It's strictly the velocity. And even though gravity technically never ends, it just gets progressively weaker with that inverse square law for the force of gravity. It's that balance point, and we look at affinity to see what would give us enough velocity to escape a planet, a body's gravitational attraction. And so this works for any mass. Interestingly, we don't have time to go into it with the time we have left, there's actually meteorites on Earth that researchers are pretty sure came from Mars. And so imagine, if you will, an asteroid, a large body striking Mars, breaking off a piece of Mars, launching it out of Mars with a high enough velocity to escape. That object gets pulled in by the Earth's gravitational force, makes it through the Earth's atmosphere, and we've actually have pieces of Mars here on Earth. Interestingly, and I've totally almost forgot about this, Mars 2020 rover launches in July. I'll be sure to remind you about that. And today being the Wednesday, the 27th of May, the first Falcon 9 with humans aboard is going to launch from Kennedy Space Center at about 4 o'clock this afternoon. I'll include that in my notes on this assignment. The weather's about 60% right now, last time I checked. And so we'll see. But this is going to be the first time we have launched Americans into space from American soil in 9 years. For the last 9 years, we've had to contract with the Russians to put astronauts up the ISS. This will be the very first time. So very exciting day. So let's look at this escape. We had a problem. We were going to determine the escape velocity from Mars. And we had a mass. We had a mass of Mars of 6.42 times 10 to the 23rd kilogram. So about 10% the mass of the Earth. Earth's about 5.97 times 10 to the 24th. So Mars is about 10 times less massive, is a better way to phrase that. Radius of Mars was 3396 kilometers. And the prudent student of physics knows all the equations are written for meters, so I rounded this a bit, just a bit. Times 10 to the 6 meters. Easy money. G is G. Wherever you see G, that's big G. 2 times 6.67 times 10 to the negative 11th. I'm going to omit units so I can squeeze this in. Mass 6.42 times 10 to the 23rd kilograms over 3.4 times 10 to the 6 meters. And I got an escape velocity of 5,018 meters per second. So an object moving that fast in the absence of air resistance. And the principle this works on is a body in motion remains in motion. So an object going that fast is going to be able to escape the gravitational attraction for the planet Mars. So let's look at something, because it's very interesting. The Earth, we're finding out, really is more and more special, oddly. So if the Earth was just a bit more massive, or its radius was a little smaller with the same mass, meaning it's more denser, we wouldn't be able to generate enough chemical energy to get off the planet. And I think that's very interesting, because we kind of take, even though rocket flight has been around only for true rockets, 100 years or so, we kind of take that for granted. If we had an Earth that was just a little more massive, or radius a little smaller, we would have a much we wouldn't be able to get off the planet. And let me just give you a comparison here. So I calculated, and hopefully, so just to escape from Earth, I calculated 11,181 meters per second. So let me just make one modification for this example. So the mass of the Earth, 5.97 times 10 to the 24th kilograms. So about 10 times more massive than Mars. Radius of Earth, 6.37 times 10 to the 6th meters. And I'm going to set up my escape velocity equation. I always recommend writing the equation first when multiplying as well. And so I talked about this on a previous video. When you got numbers with large exponents and just a coefficient there, essentially coefficient, I would go in this order. I'd multiply your numbers with your large coefficients first, and then multiply it by that coefficient. What your calculator is going to do, especially if you got a little $30 calculator like I have, it's gonna round quite significantly, and you're gonna lose some detail. So I recommend keeping those small coefficients for last. So let me change one thing. Let's say the Earth. Anybody watch The Flash? I'm gonna call it radius for Earth 2. 6.37 times 10 to the 5th meters. So a much denser Earth. Mass is the same. Radius is much smaller, so your volume is much smaller, so your density is much greater. And so let's calculate that. So again, this is Earth 1, if you will. Over Earth 2's radius, and you would get a escape velocity of 35,358 meters per second. And teammates, we would not be able to get off Earth with chemical energy. And our lives would be much, much different. So that's one thing, is this difference in, just a small difference in mass or radius would make this problematic. The other thing is, have you ever wondered how it is we can mine these metals? And we've talked about this. So the Earth went through a molten phase, and that's how we ended up with this solid iron core and this liquid core, which as it turns generates the magnetosphere. But how did we end up with how do we end up with metals near the surface close enough that we can mine iron, copper, nickel, gold? And it's fascinating, and this has just been developed in the last couple of years. You'd think people would have thought about this a long time ago. This is part of the evidence right now, only in the last few years, of this impact of another planet that used to exist in our solar system smashing into Earth, breaking off a hunk of the Earth's crust, and then forming the moon. So that's some of the leading evidence now for the impactor theory, is this hypothetical planet called Theia. When it crashed into Earth, its core went scattered around the Earth, and that's how we ended up with these mineral deposits so close to the Earth's surface. I think that's fascinating. That's just in the last couple of years. Very quickly, and we don't have a whole lot of time to go through this. I was going to take you through the rocket equation, but we need another couple of days. There's two ways. Here's my rocket. So, and you'll notice, so watch today when it launches, you got these nozzles, and it's got a restricted exit there, and that's going to help when the fuel, so here's the fuel, liquid fueled rocket, there's the fuel. As that fuel is ignited and expelled, the smaller that nozzle is, the greater the velocity. And you can look at this in two ways. You can look at this as a momentum conservation. So initially your system momentum is 0. So you got a change in momentum. So you got some momentum in the negative, not change. You got some momentum in the negative y direction, and you got some momentum in the positive y direction. So it's a momentum conservation problem on how rockets are launched. And it's this fuel is burned, but it has mass. And it has mass and it's got velocity, so that has a momentum. And because momentum is conserved, you can look at it like that. You can also look at it as a Newton's third law problem. So the force of the fuel being expelled is equal and opposite to the force on the rocket in the opposite direction. So either one of these gets you to that change of velocity of the rocket. You can either look at it as a change in momentum, and because you got some interesting things going on here, don't you? So usually you're going to have a continuous burn rate, so that can be modified. But as the fuel is burned, the mass of your rocket decreases. And watch today. So SpaceX is sponsoring. This is their rocket. SpaceX traditionally puts on the velocities on the screen. Watch that velocity tick up. We've done this in the classroom as well, if you recall. I think we did it first semester. So you can look at it either conservation of momentum or a Newton's third law problem. It's good. Tomorrow's Poco Fiesta, I'm going to ask you to manipulate the escape velocity equation. I may give you the mass of a planet, radius of a planet, and ask you for the escape velocity. I might give you a max velocity a rocket can generate, and given a mass and radius of a planet, can the rocket escape? Problems like that. It's good. All right, teammates, have you a good day. Rocket launch is about 4 o'clock, as currently scheduled, 4:11, I think, Eastern Daylight Time. Have a great day, teammates. Talk to you soon.